For our next example involving resonance structures, we're actually going to come back to one that we've already looked at. And when I said we'll talk about this later, this is later. And we're going to look at nitrate. So let's go ahead and redo the Lewis structure here, make sure we know. And one thing you may be wondering is how, I've told you that generally the first atom is going to be the central atom. But one other thing I just want to mention that your book emphasizes and that I just want to also emphasize is that if you're unsure what the central atom should be, the central atom in a Lewis structure is whatever is the atom with the lowest electronegativity. So even though nitrogen and oxygen both can form multiple bonds, nitrogen has the lowest electronegativity, so we can go ahead and put that in the middle. It's also the one that can form the most bonds out of this anyway, but that's just a good rule of thumb. Your central atom, if you're unsure, go with whatever has the lowest electronegativity. Okay, so our total number of electrons is nitrogen has 5 valence electrons. Each oxygen has 6 valence electrons. That's a multiplied sign. And then we need to add one more electron for the negative charge because this is an ion. So we'll get a total of 18 plus 5 plus 1, which gives us a total of 24 valence electrons. Now let's go ahead and draw the structure. We'll put nitrogen in the middle, our 3 oxygens around the outside, add all of our lone pairs for the oxygens. All right, and that gives us this structure. Now let's double check, do we have the correct number of electrons? Do we need to add more electrons? And if you double check, you should, if you need to pause the video and double check, but there are 24 electrons in this structure. There's 8 around each oxygen and there are 3 oxygens, so that gives us a total of 24. So we don't have any extra electrons to add, but again, our nitrogen only has 6 electrons right now around the central atom. So just like with ozone, and this is usually what we see when we get resonance structures, is there are multiple ways we could get an octet around the nitrogen in the middle. Again, we're going to be sharing electrons from the oxygen, so we could share it from this top oxygen, from this oxygen over here, or this oxygen over here. Any of these would be valid. And so that gives us 3 different resonance structures. So our resonance structures are going to look like one where there's a double bond with the oxygen on the top. And the way we indicate resonance structures is this double-headed arrow like this. We can also have a version where it's the bottom left or bottom right oxygen that formed the double bond. Or we have the version where it's the bottom left oxygen that's formed the double bond. All right, all of these give valid structures, and these are all our 3 resonance structures in this case. So resonance structures, as this example shows, are not limited to just 2. You could have 3 or 4 multiple resonance structures for a particular molecule. Again, what does this tell us about how these nitrogen-oxygen bonds actually look like? Similar to the ozone example we looked at in the last video, what we actually get is an average of all these structures. And so instead of this ion, which I forgot all these have negative charges on them, so we should indicate that. But this ion does not have one bond that's a different length than the other 2, but each of the bonds is sort of in between a single and a double bond, just like with ozone. So we see something that's kind of like this, where we have the electrons are partially shared here like this. And each of these is about, a 1 1/3 bond. Instead of being just a single bond or a double bond, those 2 extra electrons get shared across 3 bonds. And so it's sort of like 1/3 of a bond that gets shared. So that's another example of resonance structure. We've come back to this idea of nitrate, and when we first looked at this molecular ion, I said, just pick any of them. But really, all of them matter, and all of these contribute to the overall structure of this ion. And resonance can happen with even larger molecules than just these. So one really famous example of resonance that I just want to bring up, and it's mentioned in your textbook, and I think it's an important one to mention, is this quite large organic molecule. Well, large compared to what we've been talking about. So it's 6 carbons arranged in a ring like this, with 1 hydrogen off of each one. This is the molecule benzene. It has the formula C6H6. And so this is the structure. And actually this structure puzzled chemists for many years when it was first discovered. Organic chemists that were studying these carbon-based molecules weren't sure how these 6 carbons were arranged, but eventually discovered that it is in this ring structure. At this point, none of the hydrogens are all happy. They all have 1 bond, but none of the carbons are happy. We don't have enough electrons in here yet. And so one way to get the correct number of electrons in here is to include alternating double and single bonds around the carbons here. But we could swap all of these. And so there's a resonance. Let me just drag this over here. There's a resonance between this version and the version where all the double bonds are just moved over by 1 spot. And then all the hydrogens are in the same place. So resonance will continue to matter even for as you get to larger molecules. So the actual bonds in a benzene molecule are between a single and a double bond, and it's not this long short situation, but rather the electrons are sort of evenly spread across the entire ring structure here. So that's another example of resonance. We'll get lots more practice with this in homework and in class.